Welcome to qnawire.
Here we're going to be using Gauss's law to find some properties of a uniformly charged sphere with a radius of 0.04 meters. So what Gauss's law says is that the projection of the electric field outward through a closed surface, so that looks like an integral over a surface, that is equal to the enclosed charge over epsilon naught. So this law basically says that the source of an electric field is a charge, and also that it causes a divergence of the electric field from the source point. So let's see how to use Gauss's law in this case. So we have a uniformly charged sphere, and we're told the electric field outside. So what we're going to use is the field outside in order to determine the charge inside. And we can draw a little, no, we don't want to draw that one. We can draw a little Gaussian surface right at the point of the electric field. And what we know is that the electric field times the surface area of that sphere, 4 pi r squared, is equal to the entire charge enclosed over epsilon naught. So what this should be able to give us is the entire charge enclosed. And then we can turn that into a uniform charge density. So the electric field is 940 newtons per coulomb. And we also know that the electric field times epsilon naught 4 pi r squared is equal to the enclosed charge. So let's just go ahead and find that enclosed charge, and then we can turn it into a charge density by finding the volume of the sphere. Okay, so epsilon naught, the electric field we know, and we'll use SI units. Epsilon naught is just 8.85 times 10 to the minus 12, the permittivity of free space. 4 pi is just 4 pi, and we're 0.08 meters away. Having used SI units, that should give us the charge in coulombs. Let me check that. I've already checked the number a few times, but it does not hurt to check one more time. Okay, and we're getting the enclosed charge is of the order of 6.69 times 10 to the minus 10 coulombs. To find the charge density on the sphere, we simply want to divide the sum total of the charge by the volume. And the volume, of course, is 4/3 pi r cubed, with r being 0.04 meters. And that should give us the volume in cubic meters. And we get 2.68 times 10 to the minus 4. So we now have enough to find our charge density. And what that will do is govern the electric field on the inside of the sphere, as we will see by using Gauss's law for the inside. Okay, so we have our density is 2.50 times 10 to the minus 6 coulombs per cubic meter. Okay, so now we want to find the electric field inside. Specifically, at 2 centimeters from the center of the sphere. And so the big idea is that if we draw a little Gaussian surface on the inside of this sphere, it's only going to enclose the charge that's inside of that sphere. But we're going to still use the same Gauss's law that the electric field, in particular the radial component, times 4 pi r squared is equal to the Q enclosed over epsilon naught. And the charge enclosed is going to come from the density times the volume. Okay, and let me just show R is, of course, the little radius out to the Gaussian sphere, the green imaginary sphere that I drawn. So let's see. The volume is 4/3 pi r cubed. We multiply by the density, divide by 4 pi r squared from the surface area, and also the epsilon naught constant. Yeah, and some things will cancel, including 2 powers of r. So we can see why finding that density was useful. We can now solve for the electric field at any point r inside the sphere. It will grow proportionate to the radial distance from the center. Okay, so let's just numerically calculate that electric field. And again, I'll be careful with SI units, and then I should have my electric field in newtons per coulomb. And let me check one more time. And we get well over almost 2,000 newtons per coulomb. And there's an example with Gauss's law.